Mark your calendar. December 19th, 2025. It's a date that is going to mean something. Because on that day, an interstellar visitor named 3I Atlas will make its closest approach to our world. And it is not coming empty-handed. It is carrying a message, written not in radio waves or light, but in chemistry. A message that reads like the opening lines of two completely different stories. The first story is about creation. The second is about execution. And the data we have in hand right now from some of the most powerful telescopes on Earth supports both interpretations equally. This is not speculation about blurry photos or shaky signals. This is high-resolution spectrographic evidence, the kind of data astronomers stake their careers on. And it tells us that 3I Atlas is currently spraying a cocktail of molecules into the void as it tumbles toward us. Methanol, the molecular ancestor of RNA, a cornerstone of life as we know it, and hydrogen cyanide, the chemistry they use in execution chambers, both streams emanating from the same object, heading in our general direction. So the question posed by Harvard astrophysicist Avi Loeb is the one that should hang in the air tonight. Is 3I Atlas a friendly gardener, arriving to plant the seeds of life across our solar system? Or is it a serial killer, dusting our planet with poison? The ambiguity is where the real story begins, and you need to stay until the end, because what happens, or doesn't happen on December 19th, might fundamentally redefine what we think is possible in this universe. The chemistry is already on its way, and if you find yourself as captivated by these questions as I am, if you feel that chill of a mystery unfolding in real time, then consider subscribing right now. As December 19th approaches, and this story develops hour by hour, I want you along for the ride. Leave a comment. Tell me where you are in the world right now, what hour you're listening to this, and whether you think 3I Atlas is exactly what the astronomers say it is, or something we have not yet fully understood. Let's start with the payload, the bombshell. The data from ALMA, the Atacama Large Millimeter Array, and what it reveals about a methanol surge and a two-valve problem. You need to understand this clearly. Methanol is the chemistry of life, cyanide is the chemistry of death, and 3I Atlas is shedding both. Let me say that again, slower this time, because the weight of it needs to land. An object that originated beyond our solar system, tumbling through the void for who knows how long, is currently spraying a cocktail of molecules into space that reads like a recipe for both creation and annihilation. ALMA has been watching this thing since the late summer of 2025, and what it found should make every person on Earth stop and ask a simple, chilling question. What exactly is this thing doing? The timeline matters here, so let me give it to you clean. August 28th, 2025. ALMA detects methanol, chemical formula CH3OH, streaming off 3I Atlas. September 18th and 22nd, more methanol detection, stronger this time. October 1st, methanol again, consistent and powerful. Now rewind slightly. September 12th and 15th, ALMA picks up hydrogen cyanide, HCN, the same poison used in gas chambers, emanating from the same object. These are not vague impressions or controversial interpretations of fuzzy data. These are spectrographic measurements, the kind of evidence astronomers trust with their careers. The molecules are there. The question is why? The production rate ratios tell us something is deeply wrong here. In typical cometary chemistry, you expect certain molecules to appear in predictable proportions based on how ice sublimates in sunlight. Think of it like baking. If you follow a recipe, the ingredients come out in roughly the same ratios every time. But 3I Atlas is not following the recipe. Measurements show methanol to hydrogen cyanide ratios hovering around 124 in some observations, 79 in others. To put that in perspective, most comets we have studied show ratios nowhere near this extreme. There is a precedent, one lonely precedent, a comet called C-2016R2, which also had bizarre chemistry, but that was an oddball from our own solar system. This is an interstellar visitor doing the same thing, and that coincidence should unsettle you. But ALMA didn't just detect these molecules, it mapped where they are coming from. And that is where the story gets mechanical, where the narrative of a simple comet begins to fray. Hydrogen cyanide appears to be venting from the nucleus itself, the solid core of the object, what we might call the hull if we were feeling speculative. Methanol, on the other hand, is forming far from the nucleus, more than 2,500 kilometers away, out in the plume where molecules are supposed to break down, not build up. This is the two-valve hypothesis. One valve on the hull spewing cyanide, another valve, or perhaps a distributed chemical process, generating methanol in the wake. If you were designing a spacecraft with two separate exhaust systems, one for propellant and one for cargo, this is exactly the signature you would expect to see. Standard sublimation models, the ones we use to predict how ice behaves when sunlight hits it, cannot reproduce this pattern. Normally, volatiles like methanol should sublimate symmetrically or enhance on the sunward side where heating is strongest. The models follow power law scalings, mathematical relationships that describe how production rates change with distance from the sun. Typical comets fall somewhere between 2 and 4 on that scale. 3i Atlas clocks in at 5.2. That number is an outlier. It screams that something other than simple ice melting is happening here. We'll unpack what 5.2 actually means in a later part, but for now, just know this. The object is behaving in a way that our textbooks do not cover. So, here is the narrative tension that should keep you awake tonight. Exhaust versus cargo. If one molecule looks like propellant residue and the other looks like biological feedstock, what does that imply? Imagine a spacecraft, and I am being deliberately speculative here, spewing reaction mass out one end to adjust its trajectory while simultaneously jettisoning containers of prebiotic chemicals out the other. That is the image the ALMA data conjures, whether we like it or not. Methanol is a precursor to formaldehyde, which leads to ribose, which is the sugar backbone for RNA. It's also the favorite meal of methylotrophic bacteria, microbes that eat alcohol for breakfast. Hydrogen cyanide, in the right doses, can participate in amino acid synthesis and even trigger seed germination in plants. In the wrong doses, it shuts down cellular respiration and kills you. Both molecules together, in this configuration, paint two completely opposite pictures. Now, before you accuse me of jumping to alien megastructures, let me give you 3 natural explanations. First, heterogeneous nucleus composition. Maybe 3i Atlas is a cosmic layer cake, with different ices frozen in different regions, and as it tumbles and heats, different layers expose themselves and vent different chemicals. Second, clathrate structures. These are molecular cages where one molecule traps another inside an ice lattice. When clathrates break apart, they can release trapped gases in bursts that look unusual. Third, thermal processing. Maybe the object spent time near a star in its home system and underwent chemical reactions that baked methanol into its structure while leaving cyanide in volatile pockets. All 3 of these are plausible. None of them fully explain why the sourcing is so asymmetric, why cyanide comes from the core and methanol appears far downstream. I need to be honest about ALMA's limits. The array can only observe when the object is at certain angles relative to the sun, and it cannot see everything at once. There are data gaps, periods when 3i Atlas was too close to the sun in our sky for ALMA to track it safely. The resolution is remarkable, but not infinite. It can map the near-field coma, the region close to the nucleus. But the full heliospheric wake, the trail stretching millions of kilometers behind the object, is beyond its reach. So when I say ALMA found asymmetric venting, I mean it found asymmetry in the regions it could observe. The full picture is still developing. December 19th is coming. The geometry of that flyby matters more than distance alone, and we're going to show you exactly why Earth might still taste the wake, even from 270 million kilometers away. This is not just about an object passing by, it's about whether we are standing downwind. Let's talk about December 19th, the day of closest approach. The narrative in the mainstream news is very simple, very clear, and designed to be comforting. NASA and the European Space Agency have been unequivocal. There will be no impact. 3I Atlas will pass at a distance of roughly 1.8 astronomical units, about 270 million kilometers. Its trajectory is well understood. The math is solid. It is not going to hit us. And that is true as far as it goes. But impact is the crudest, most primitive way an object can affect a planet. It is a blunt force trauma. What we are dealing with here is something far more subtle, far more insidious, or far more generous, depending on your point of view. It is about chemistry and geometry and the invisible rivers that flow through our solar system. To understand why, scale down the cosmos. Imagine Earth as a marble and 3I Atlas as a truck driving past you at highway speed. Except this truck is leaking a fine, persistent mist out of its back end. The truck does not hit you. But if you are standing downwind, you are going to breathe some of that mist. You are going to taste it. Now scale that back up to astronomical units and add in solar wind, magnetic fields, and charged dust particles. You start to see the problem, or the opportunity. The question for December 19th is not whether 3I Atlas will crash into us. The question is whether Earth will pass through any portion of the chemical wake it is leaving behind. Orbital geometry is three-dimensional, and most of the diagrams you see flatten it into 2 dimensions, which hides the profound complexity. 3I Atlas is on a hyperbolic trajectory, meaning it is moving fast enough to escape the solar system entirely after this flyby. Its orbital plane is inclined relative to Earth's orbit. The 2 paths do not lie in the same flat sheet. Instead, they are skewed like 2 highways crossing at different elevations, one an overpass, the other tunneling below. But the wake is not a thin line. It is a cone, a plume, a diffuse cloud of molecules and dust spreading outward as the object moves. The solar wind pushes on that cloud. The interplanetary magnetic field threads through it, and depending on how those forces align, portions of the wake can drift far from the object's geometric trajectory. Here is the critical clue from ALMA. Hydrogen cyanide is depleted on the sunward side of 3I Atlas and enhanced elsewhere. Methanol shows the opposite pattern, stronger in certain directions, weaker in others. This sunward asymmetry tells us the venting is not random, it is directional. If you imagine the object as a sprinkler, it is not spraying evenly in all directions. It is pulsing jets from specific locations, and those jets are pointed somewhere. The question we must answer is simple, and it has profound implications. Does Earth's path through space cross the methanol-rich sector, the cyanide-rich sector, or some unsettling blend of both? This is where things get unnerving. Charged dust and nanograins, particles so small they're almost molecular, can couple to the solar wind and the interplanetary magnetic field. When that happens, they stop following simple ballistic trajectories and start hitching rides on magnetic field lines. Think of them as microscopic rafts floating on invisible rivers. Those rivers can curve, twist, and redirect particles in ways that pure gravity and momentum cannot explain. We've seen this happen with volcanic plumes on Earth. Ash and aerosols get caught in upper atmospheric currents and travel thousands of kilometers downwind, far beyond where simple physics would predict. The same principle applies in space, except the currents are made of plasma, and the distances are measured in astronomical units. Let's talk numbers. Rough back-of-the-envelope calculations, but numbers nonetheless. If 3I Atlas is releasing methanol and hydrogen cyanide at the rates ALMA measured, and if those molecules expand into a spherical shell as they move away from the nucleus, then by the time they reach Earth's orbital distance, the concentration will have dropped by a factor of roughly 1 trillion. That is dilution on a cosmic scale. To reach lethal concentrations of hydrogen cyanide in Earth's atmosphere, you would need the object to release amounts orders of magnitude higher than what we are seeing. So the mainstream position, and it is a reasonable one, is that dilution kills the risk. By the time any of this reaches us, it will be so spread out it is functionally irrelevant. But, and this is a monumental but, that assumes uniform dispersion. It assumes the wake spreads evenly in all directions like a perfect thinning sphere and does not get concentrated by magnetic funneling or solar wind channeling. If a coronal mass ejection from the Sun happens to align with Earth's magnetosphere at the precise time 3I Atlas passes, you could get a temporary filament, a narrow, concentrated stream of particles nudged in our direction. The odds are low, but they are not zero, and if it happens, the concentration in that filament could be much, much higher than the average dilution factor suggests. This is speculative. I want to be clear about that. But it is not physically impossible. ALMA's angle-resolved spectra show directional biases in the molecular emission. Certain velocities, certain Doppler shifts are stronger than others, which means the molecules are moving preferentially in specific directions. But remember, ALMA maps the near field, not the full wake. It tells us what is happening within a few 100,000 kilometers of the nucleus. It does not tell us what happens 10 million kilometers downstream, or 100 million, where Earth will be. That is the observational gap we're living in right now. Solar activity is unpredictable on short timescales. A coronal mass ejection can erupt with a few hours' notice or no notice at all. If one happens in mid-December, and if the magnetic field geometry is just right, particles from 3I Atlas could be shepherded along field lines in ways that defy simple ballistic models. I'm not saying this will happen. I am saying it is a scenario worth considering, especially when the chemistry involved includes both a precursor to life and a cellular poison. So December 19th is not just a date on a calendar, it is a geometric event. It is the moment when Earth's orbit intersects the projected zone where 3I Atlas's wake might be drifting. Whether anything actually reaches us depends on factors we cannot fully predict yet. Solar wind speed, magnetic field orientation, the exact release rates, and velocity distributions of the molecules ALMA detected. We are flying partially blind here, and that should make you uncomfortable, or curious, or both. Next, we need to dig into what those molecules actually mean. Why does this specific chemical combination fuel two diametrically opposite stories? The friendly gardener versus the serial killer. Both interpretations are sitting right there on the same data, and that is where things get truly strange. Friendly gardener versus serial killer. It's a stark dichotomy, a narrative fork in the road laid out by the chemistry itself. Avi Loeb, the Harvard astrophysicist who brought you Oumuamua as a potential alien light sail, frames 3I Atlas with this exact thought experiment, a question of intent versus natural accident. Is this object a benevolent entity arriving to seed our solar system with the building blocks of life? Or is it a malignant one, dusting Earth with poison? Frustratingly, brilliantly, the ALMA data supports both narratives with almost equal weight. Let me show you how. First, the gardener. Methanol is an astrobiological superstar. If you wanted to build the molecules of life from scratch, methanol is one of the best starting points you could ask for. Under the right conditions, it oxidizes into formaldehyde. And formaldehyde is a key ingredient in the Formose reaction, a chemical pathway that produces ribose, the 5-carbon sugar that forms the backbone of RNA. Ribose is not optional in biology as we know it. It is fundamental. Methanol is also the primary carbon and energy source for methylotrophic bacteria, microbes that thrive in environments where most other life would starve. If you wanted to kickstart prebiotic chemistry on a sterile planet, or give a nascent biosphere a metabolic boost, dumping methanol into the environment is a very efficient way to do it. Laboratory experiments have shown that methanol, when exposed to ultraviolet radiation or energetic particles, can trigger cascades of reactions that build increasingly complex organic molecules, sugars, amino acids, nucleotide precursors. All of it can start with methanol. Now, the serial killer. Hydrogen cyanide has a reputation. It is the stuff of spy novels and execution chambers, a molecule that binds to the iron in your cell's cytochrome oxidase enzymes and shuts down your ability to use oxygen. In bulk, it is lethally efficient. But, and this is where the dual nature reveals itself, in trace amounts, hydrogen cyanide is not a poison. It is a participant. Cyanide chemistry is involved in the Strecker synthesis, one of the primary pathways for making amino acids under prebiotic conditions. It also shows up as a seed germination trigger for certain plants. The dose makes the poison. A little cyanide in the right place at the right time can be beneficial. A lot of cyanide in the wrong place is catastrophic. The difference is concentration, timing, and context. So, here is the dual function delivery hypothesis, and I want to mark this clearly as speculative. What if both molecules are intentional? What if the hydrogen cyanide is there to clear ecological niches, to suppress existing microbial competitors or sterilize certain zones, while the methanol is there to feed the colonizers that follow? It would be a 1-2 punch. First, you disrupt the existing equilibrium. Then you provide abundant resources for the organisms you want to establish. You are not just planting a garden, you are preparing the soil aggressively. Alternatively, and this is the strictly natural explanation, both molecules could simply be byproducts of the same chemical reaction cascade happening on the object's surface. Irradiation of organic ices can produce both methanol and hydrogen cyanide simultaneously. No intent required. Just physics and chemistry doing what they do, mindlessly, across the cosmos. Let's lay out the models. The natural comet model. Expected observables would include symmetric or slightly asymmetric venting, production rates that follow known sublimation curves, and molecular ratios consistent with other comets. ALMA's maps partially match this, but the extreme methanol to hydrogen cyanide ratios and the stark spatial separation of sources are harder to explain. The engineered tanker model, expected observables would include precisely controlled release rates, directional venting that does not correlate with solar heating, and possibly non-gravitational accelerations as the object adjusts its trajectory. We don't have confirmed evidence of non-gravitational accelerations yet, but we also haven't ruled them out. Then there's the hybrid model, a natural body with catalytic surface chemistry. Expected observables would include unusual molecular ratios, steep power law dependencies on solar distance, and time-variable production rates. ALMA found all of these, so the hybrid model, where a natural object undergoes chemically enhanced reactions on its surface, might be the best fit for the data we have right now. But the ambiguity persists. If this is panspermia, the natural seeding of life, why both molecules? If it is a toxin delivery system, why so much methanol? The gardener carrying weed killer analogy is cute, but it doesn't resolve the tension, it just highlights it. You could argue that a sophisticated seeding operation would include both enabling and disabling agents to maximize the chances of successful colonization. You could also argue that nature produces complex chemical mixtures all the time, and reading intent into them is a profound category error. Both positions are defensible with the current data, and that is the problem. or the opportunity, depending on whether you are a scientist demanding proof or a storyteller sensing a paradigm shift. There's another layer: detectability. If 3I Atlas were carrying spores, dormant microbes, or complex organic polymers, we would not see them in ALMA's spectra. ALMA detects gas phase molecules, not solid particles, and certainly not microscopic biological structures. The imaging we have from optical telescopes shows a fuzzy blob, not a detailed surface. Even if there were macroscopic structures, panels, grids, geometries, we would not resolve them at this distance with current instruments. In situ sampling would change everything. A probe that could fly through the coma, collect dust grains, analyze their composition, sequence any organic polymers, that would give us definitive answers. But we don't have that probe. We have ALMA. And ALMA gives us chemistry, not biology. So here is the measured scientific verdict. We need more data. ALMA has given us a chemistry puzzle that is genuinely uncanny, genuinely strange. But extraordinary inferences require extraordinary proof. The data supports multiple interpretations. And until we can eliminate some of those interpretations with new observations, we are stuck in the ambiguity. That is not a satisfying answer, but it is an honest one. What we know for certain is that 3I Atlas is chemically unusual. What we do not know is why. And before you think Earth is the only target worth considering, let me ask you this. What if 3I Atlas is not aiming at us at all? Earth, for all its vibrant beauty, might not be the most interesting piece of real estate in the solar system. Not if you're an interstellar entity trying to seed life. Think about it. Our planet is a crowded, biochemically noisy, and fiercely competitive environment. Billions of years of evolution have filled every niche. Introducing a new organism here is like trying to start a campfire in a rainforest during a monsoon. The odds are stacked against it, but there are other places, blank slates, protected environments, prime real estate for a gardener, specifically Europa, or Enceladus, or any of the other icy moons with subsurface oceans. Let me explain why an interstellar carrier, if that is what this is, might be infinitely more interested in them than in our pale blue dot. Europa, Jupiter's fourth largest moon, is a world encased in a global shell of water ice. Beneath that shell, however, is not frozen silence, but a liquid ocean. An ocean with twice the volume of all of Earth's oceans combined. It is kept liquid by tidal heating, the relentless gravitational squeeze Jupiter exerts on Europa as it orbits. The surface is frozen and radiation blasted, a sterile wasteland. But beneath that ice, there is liquid water, dissolved minerals, and possibly hydrothermal vents. If you wanted to plant the seeds of life somewhere protected, somewhere with steady energy sources and pristine chemical gradients, Europa is a far better candidate than Earth's surface. An icy moon offers a blank slate. A place where introduced organisms would not have to compete with billions of years of evolutionary incumbents. You wouldn't need to clear a forest. You'd be planting in fresh, fertile soil. Orbital mechanics makes this more plausible than you might think. 3I Atlas is on a hyperbolic trajectory that will take it past Earth and then onward through the solar system. If its velocity and direction are right, and if it can make small adjustments, it could continue toward the Jupiter system with relatively low delta V requirements. Delta V is the change in velocity needed to alter a trajectory, and in space, delta V is currency. The less you need, the more feasible the mission. A gravitational assist from Earth or Mars could provide some of that delta V for free, nudging the object toward Jupiter without requiring additional propellant. This is speculative, but it is not physically absurd. Our own missions to the outer solar system use gravitational assists all the time. Now, consider methanol's role in a subsurface ocean like Europa's. Under those conditions, high pressure, low temperature, bathed in radiation flux from Jupiter's powerful magnetosphere, methanol could act as both a carbon source and an energy source for chemosynthetic ecosystems. Chemosynthesis is the process by which organisms derive energy from chemical reactions rather than sunlight. On Earth, entire thriving ecosystems around deep-sea hydrothermal vents are based on chemosynthesis. Similar processes could theoretically occur in Europa's dark ocean. Methanol, when oxidized or reduced in the presence of minerals and radiation, can release energy and produce more complex organic molecules. It is, in essence, a starter fuel for biochemistry in dark, isolated environments. This leads to the critical question: intentional targeting versus a random pass. The probability of an interstellar object randomly intersecting Jupiter's gravitational sphere of influence is low, but not zero. We've seen 2 confirmed interstellar visitors now, Oumuamua and 2I Borisov. Statistically, we expect more. But 3I Atlas's chemistry and venting behavior do not look entirely random. The directional asymmetries, the bizarre molecular ratios, the steep power law scaling. These are features that make you wonder if the object is following a programmed sequence rather than passively responding to solar heating. If it is programmed, then targeting becomes a possibility. If it is natural, then any intersection with Europa would be a cosmic coincidence. Let's entertain the bioassessment idea, purely as a thought experiment. December 19th, Earth's closest approach, could be a scan, a way for the object, or whatever mechanism controls it, to test whether Earth is biochemically hospitable before committing resources to a deeper insertion into the solar system. What signals would an advanced probe look for? Atmospheric composition. Oxygen and methane together are a strong biosignature because they react with each other and shouldn't coexist in equilibrium unless something is continuously replenishing them. Electromagnetic anomalies, radio transmissions, modulated signals, anything that suggests a technological civilization. Surface patterns, indicators of liquid water and seasonal cycles. If the object had sensors and could process that data, it could make a go-no-go decision about whether to adjust its trajectory toward a secondary, more promising target like Europa. The counterpoints are substantial. Targeting an ice moon requires precision. You need to know where the moon will be in its orbit at the time of your arrival, and you need to adjust your velocity vector to match. That requires propulsion, navigation, and some form of onboard computation or pre-programming. The energy requirements are not trivial. Even a small course correction at interstellar distances requires significant delta V. And we have not seen evidence of large-scale propulsion events. The object is venting molecules, not firing rockets, at least not in any way we have confirmed. How could we test this? Observational tests could settle it. If 3I Atlas changes its venting pattern after planetary flybys, that would be significant. If we detect fragments or secondary objects separating from the main body and trending toward Jupiter, that would be extraordinary. Spectroscopic follow-ups in the coming months, wide-field imaging surveys tracking the object's trajectory, these are the methods we should be using to monitor for anomalies. If the object is natural, it will continue on its hyperbolic path and fade from view. If it is something else, it will give us more clues. But there is another possibility, one that is both more mundane and, in its own way, more disturbing. It reframes the entire narrative. What if the hydrogen cyanide is not a weapon and not a prebiotic feedstock? What if it is just exhaust? Let's revisit the serial killer interpretation from a completely different angle. What if cyanide is not a weapon, but exhaust? Let me be very clear up front. This is speculative, and it invokes chemistry that is unusual, possibly exotic, and certainly not something we have direct evidence for. But the question is worth asking because it cuts through the narrative of intentional poisoning and replaces it with something equally staggering: the signature of a machine. Hydrogen cyanide can be produced in high-temperature oxidative or catalytic environments. If you burn hydrocarbons or amines in the presence of nitrogen, you can get nitriles, including hydrogen cyanide, as byproducts. Certain hypothetical thermochemical thrusters, engines that rely on chemical reactions to generate thrust, might produce exactly this kind of exhaust. Imagine an engine that uses organic carbon and nitrogen-rich compounds and oxidizes them in a controlled burn. The primary products would be carbon dioxide and water vapor. The secondary products, the chemical smoke, could include hydrogen cyanide, ammonia, and other nitrogen-bearing molecules. If 3I Atlas had an engine like that, and if it were using it to make small, precise trajectory corrections, the hydrogen cyanide we are seeing might not be cargo or a payload. It might be the leftover smoke from the engine. Remember ALMA's map. Hydrogen cyanide is depleted on the sunward side of the object. If the cyanide were sublimating passively from the surface, you would expect more of it on the sunward side, where the solar heat is strongest. But we see the opposite. It is stronger on the anti-sunward side, or at least stronger in specific directions that do not correlate with solar illumination. That pattern makes perfect sense if the cyanide is being vented from specific locations, like thruster ports, rather than evaporating uniformly from the surface. The active regions could be on the shaded side, shielded from solar heating, with the venting driven by internal, engineered processes. Natural analogues exist, but they are imperfect. Some solar system comets, like 67P Churyumov-Gerasimenko, show asymmetric jets tied to specific geological features. Cliffs, pits, and fractures can focus volatile release into narrow beams. But 3I Atlas's asymmetry is more pronounced, and the molecular composition is more unusual. Comparing ALMA maps of 3I Atlas with maps of other comets shows differences in both the spatial distribution and the intensity of the emissions. The jets on 3I Atlas seem more directional, more organized, and that organization is what raises eyebrows. Here is the engineering thought experiment, a vehicle shedding low-mass molecular exhaust to adjust its attitude, its orientation in space, while simultaneously carrying a separate reservoir of organic cargo. The exhaust would be optimized for momentum transfer, which means high velocity, low molecular weight particles. Hydrogen cyanide fits that profile. It's light, easy to accelerate, and carries kinetic energy efficiently. The cargo, methanol, would be stored in a different compartment and released separately, possibly from different vents or through a different mechanism. This is how you would design a dual-purpose mission: propulsion and payload delivery in one integrated package. The feasibility issues are significant. Mass budgets, reaction energetics, these are all constraints that would limit what you could do with a chemically propelled interstellar vehicle. But they are not insurmountable, especially if the technology level is higher than ours. Signatures of propulsive behavior would show up in the data if they existed. Non-gravitational accelerations, deviations from the path predicted by gravity alone, anomalous light curve periodicities, recurring jet patterns that happen at regular intervals or in response to specific conditions. So far, we do not have confirmed reports of any of these. The object appears to be following a standard hyperbolic orbit, and its brightness variations seem consistent with a tumbling, irregularly shaped body. But absence of evidence is not evidence of absence. We have not been monitoring 3I Atlas continuously, and subtle accelerations might not show up in the limited data we have. If hydrogen cyanide is exhaust and methanol is cargo, then we are looking at a machine. Or we are looking at nature doing such a convincing impression of a machine that we cannot tell the difference. That ambiguity, that uncertainty, is where the real tension lives. Science demands skepticism, but it also demands openness to possibilities that seem absurd until they are not. Oumuamua taught us that. 2I Borisov taught us that. And now, 3i Atlas is teaching us that the line between natural and artificial, between chemistry and engineering, is thinner than we ever thought. This leads us to a deeper mystery, one buried in a single staggering number. 5.2, the methanol power law mystery. This is where the data points squarely at something extraordinary. ALMA reports that methanol production from 3i Atlas scales roughly as the heliocentric distance, r to the power of 5.2. In plain language, as 3i Atlas gets closer to the Sun, its methanol output increases at a rate that is explosively, unnaturally fast. That exponent, 5.2, is a number that should not exist in a natural, sublimating body. Power laws describe how one quantity changes in relation to another. In comet science, we use them to predict how the production of volatiles, molecules like water, carbon monoxide, methanol, changes as the comet heats up. Think of an oven. The closer you get to the heat source, the faster ice melts. But the relationship isn't linear. It follows a power law. For typical comets, the exponent ranges from about 2 to 4. Water ice is usually around 3. Methanol, being intermediate, should fall somewhere in that comfortable range. But 3i Atlas gives us 5.2. That is steeper than anything we normally see. It screams that something other than simple ice melting is driving this methanol release. Let's walk through 3 natural models and see why each one struggles. Pure sublimation. If methanol ice was simply sitting on the surface, absorbing sunlight and turning directly from solid to gas, you'd expect an exponent closer to 3 or 4. The steeper exponent suggests heating alone isn't enough. Devolatilization of clathrates. These ice cages can release trapped gas in bursts, but even clathrate decomposition typically produces exponents in the 3 to 4 range. You'd need a very specific, massive reservoir to push it to 5.2. Thermal cracking of organics. If complex organics on the surface are breaking down into methanol as they heat, that could work. But thermal cracking is usually a gradual process, not a runaway one. The exponent should reflect that gradual increase, so we arrive at the runaway catalysis hypothesis. This is where it gets fascinating. Imagine a surface catalyst, a specific mineral or microstructure that, once heated by sunlight, triggers an exothermic reaction. Exothermic means it releases heat. That released heat further accelerates the reaction, which releases more heat, creating a violent feedback loop. Methanol production goes into overdrive, not because the sun is heating the ice faster, but because the ice is heating itself through chemical reactions. If you've ever seen a pile of damp hay spontaneously combust, you've seen this principle. Decomposition releases heat. Heat accelerates decomposition, and suddenly, you have a fire. On 3i Atlas, the feedback could be chemical rather than combustive, but the mathematics of a runaway system would be similar. Runaway systems produce steep power laws because small changes in temperature trigger enormous, non-linear changes in reaction rates. Laboratory analogues exist, sort of. When you irradiate organics with UV or energetic particles, you can trigger secondary chemistry. Methanol can form from carbon monoxide and hydrogen under irradiation. Formaldehyde can decompose. These reactions can show non-linear temperature dependence, thresholds, activation energies that, once crossed, cause production rates to spike. If 3i Atlas has a surface rich in such reactive materials, and if those materials are being activated as the object approaches the sun, you could get the 5.2 power law. Observational tests that would support runaway catalysis include time-dependent spectral changes, abrupt spikes in methanol lines, correlated thermal emission, hotspots on the surface coinciding with methanol vents, and production rate surges that don't correlate with steady solar heating. ALMA has the resolution to detect some of this, but whether it did in its limited windows is unclear from public data. We need more detailed time series analysis. An alternative engineered scenario involves an internal reagent bank. Imagine sealed containers or reservoirs inside the object, triggered by heat or sunlight. Once the seals break or valves open, reagents mix, react, and produce methanol in a controlled, cascading release. The steep power law could reflect the opening sequence of those reservoirs, with more of them activating as the object gets closer to the sun. This sounds like science fiction, and maybe it is, but the energetics are not prohibitive. A few tons of reactive chemicals could produce the methanol output ALMA measured. The implications are profound either way. If this is natural, we've discovered a new class of hyperreactive comet, an object that undergoes catalytic surface chemistry that our standard models cannot predict. That's a major finding in planetary science. If this is engineered, if the object demonstrates controlled, triggered release mechanisms, then we are looking at technology, and that would be the biggest discovery in human history. Both conclusions rest on the same data point. 5.2, a number that should not exist, but does. This forces us to ask, where could such an object have even come from? The interstellar disk hypothesis. To explain the chemistry without invoking engineering, we must look to the birthplace of 3I Atlas. Protoplanetary disks, the swirling clouds of gas and dust around young stars that eventually form planets, vary wildly in composition. Some are carbon-rich, some oxygen-rich, and a rare subset are methanol-heavy. If 3I Atlas formed in a methanol-heavy disk, that would explain its extreme chemistry without needing anything exotic. Methanol forms in space through surface chemistry on cold dust grains. Carbon monoxide lands on a grain, gets hydrogenated by hydrogen atoms, and becomes methanol. This happens over millions of years in the dense, cold regions of molecular clouds. When a star and disk form, they inherit this chemistry. If the parent cloud was particularly rich in carbon monoxide and hydrogen, the resulting disk, and the planetesimals that form within it, would be methanol-rich. Our closest analogue is Comet C 2016 R2. This comet, from our own solar system, had unusually high abundances of carbon monoxide and nitrogen, along with elevated methanol. Its composition suggested it formed in a colder, more carbon-rich environment than typical. The parallels to 3I Atlas are suggestive. If a comet from our system can have such unusual chemistry, then an interstellar visitor from a completely different stellar nursery could have even more extreme ratios. Here's a plausible, purely natural origin story. In another star system, light years away, a protoplanetary disk rich in methanol and organics formed planets and moons. One of those icy bodies, a Kuiper belt analog, had a methanol-rich veneer. Through gravitational interactions, a migrating gas giant, or a passing star, that icy body was ejected from its home system. It spent millions or billions of years drifting through interstellar space, accumulating cosmic ray damage, until it entered our solar system on a hyperbolic trajectory. That body is 3I Atlas. Its chemistry is a fossil record, a snapshot of a disk we will never directly observe. Isotopic signatures would settle this question decisively. Isotopes, versions of elements with different numbers of neutrons, are diagnostic of the temperature and environment where a molecule formed. Deuterium to hydrogen ratios, carbon-13 to carbon-12 ratios, nitrogen-15 to nitrogen-14 ratios. If 3I Atlas shows deuterium enrichment, it suggests formation in a very cold environment, possibly the outer regions of a disk, or even the interstellar medium itself. If its carbon isotope ratios differ from solar system values, that proves it formed around a different star. ALMA can measure some isotopic lines, but it requires long, dedicated observations. Future millimeter wave observations should prioritize this. They are the fingerprint that will tell us where this thing came from. The consequences of a methanol-rich origin go beyond this one object. If interstellar chemistry is this diverse, then the seeding of prebiotic molecules across the galaxy may be more common than we thought. Every star system could be receiving a slow rain of organic-rich fragments from other systems. Panspermia, the natural spreading of life's ingredients, doesn't require a gardener if the garden seeds itself, but objections exist. Methanol-heavy objects might be rare, even in methanol-rich disks. Our detection is biased. We see the bright, active, close objects, not the typical ones. 3I Atlas might be a 1 in a billion outlier. We simply don't have enough interstellar visitors to know what typical looks like. What should we watch for? The James Webb Space Telescope, JWST, has the sensitivity to detect key isotopes. Long baseline ALMA mapping could reveal finer details of the molecular kinematics. And of course, a rendezvous mission, a probe sent to intercept 3I Atlas before it leaves, would give us direct samples. That's the gold standard. Until then, we are making educated guesses based on remote sensing. But while we're guessing, let's ask one more truly strange question. We've framed cyanide as poison, as exhaust, as a prebiotic ingredient. But what if it's something else entirely? What if it's an anesthetic? The opioid sedation theory. Label this upfront as fringe, speculative, and possibly absurd. But the idea is chemically compelling enough that it deserves examination, if only to understand why it ultimately fails as a likely scenario. Hydrogen cyanide, at low concentrations, doesn't just kill, it alters biochemistry. In mammals, low-dose exposure affects neurotransmitter systems. It interferes with dopamine metabolism, alters serotonin pathways, and can produce effects ranging from euphoria to stupor. In microbes, cyanide can inhibit specific metabolic pathways without causing immediate cell death. The organism slows down, becomes less competitive, less aggressive in resource acquisition. This isn't sedation in the human sense, but it's metabolic suppression. The functional result is similar. An organism exposed to low-dose cyanide is easier to outcompete. Here's the speculative mechanism. Low-dose hydrogen cyanide acts to suppress aggressive or competitive actors in a biosphere, clearing ecological niches for colonizing microbes. If you were seeding a planet with your own organisms, you'd want to give them an advantage. One way is to suppress the existing biology, not kill it outright, but slow it down, make it less able to defend its territory. Then, the methanol comes in as the feedstock for your colonizers. The methylotrophs that can metabolize the alcohol and thrive precisely where other organisms are struggling. It's a surgical, 1-2 punch designed to shift the ecological equilibrium, not wipe the board clean. Plausibility, however, requires brutal calculation. What atmospheric concentrations of hydrogen cyanide would be needed to affect microbes? To produce measurable metabolic suppression in bacteria, you need concentrations in the parts per million range in their immediate environment. In Earth's atmosphere, that would require deposition rates astronomically higher than what ALMA suggests 3I Atlas is releasing. To affect mammals, you'd need even higher concentrations over larger areas. The whole Earth sedation idea is numerically implausible. The dilution factors are too extreme, and atmospheric mixing is too fast. And here's the interesting twist. Magnetospheric and ionospheric interactions could concentrate particles. Earth's magnetic field funnels charge particles toward the poles, creating the auroras. If hydrogen cyanide molecules or cyanide-bearing dust grains were ionized, they could follow similar paths. You could get localized enhancements in the upper atmosphere at high latitudes, where concentrations might be orders of magnitude higher than the global average. Whether that would be high enough to affect biology is still extremely questionable, but it's less implausible than whole planet exposure. This connects to dark historical and ethical thought experiments about chemical agents. Humans have used sedatives, paralytics, and incapacitants. The idea of suppressing a population before colonization is not alien to our own behavior. Repeating those analogies in a cosmic context is ethically charged. I am not advocating for this interpretation. I am presenting it as a narrative possibility, a way to think about the chemistry, not as a factual claim. Epistemic reminder. This is compelling for storytelling. It is weak for hard science. There is no evidence of atmospheric transport, no measurements of cyanide spikes correlating with 3I Atlas's approach, and no biological signals to support it. It is a thought experiment, and it should remain one unless new data forces our hand. Let's take the gardener metaphor more seriously. If you were to design a cocktail to terraform, to rewrite a biosphere from scratch, what would it look like? Terraforming cocktail, methanol and cyanide as a biosphere rewrite primer. What if the gardener isn't planting us, but planting something tailored to a completely different biochemistry? Let me be clear. This is speculative framing, a narrative device. But the chemistry reads like a recipe for ecosystem engineering if you squint. Methanol supports methylotrophs, versatile, resilient bacteria that can establish themselves in harsh environments. Cyanide, meanwhile, selectively suppresses organisms that lack cyanide resistance pathways. Many bacteria and archaea have enzymes to detoxify cyanide. Those without are at a severe disadvantage. Release both together, and you create a powerful selective pressure. Methylotrophs with cyanide resistance flourish. Everything else struggles. Conceptualize the steps. Input. Methanol delivered by 3I Atlas. Primary colonizers. Methylotrophic bacteria with cyanide resistance. Establish biofilms. Consume methanol and alter local chemistry, pH, oxygen, byproducts. Ecosystem change. The colonizers modify the environment to suit their metabolism, creating niches for secondary organisms. The end result is an ecosystem that looks different from the original, not because it was destroyed, but because it was outcompeted and reshaped. The technical hurdles for such engineered terraforming are astronomical. Dose control across interstellar distances is nearly impossible. Persistence of the reactive molecules is low. Unintended consequences in complex ecosystems are unavoidable. Yet, the concept isn't new. Directed panspermia, the idea that life on Earth was intentionally seeded, was seriously proposed by scientists like Francis Crick. Modern debates on planetary protection grapple with the same questions in reverse. What if we are the ones being seeded? A plausible timeline if seeding were attempted. Chemical effects would be immediate, days, weeks. Microbial colonization would take years to centuries, and full ecosystem shifts would require millennia. We have observed none of this. No sudden microbial blooms, no anomalous shifts in atmospheric trace gases. So if this is terraforming, it's either in the earliest undetectable stages or it hasn't started. Detection signals to watch for would include sudden shifts in atmospheric methane or other trace gases, emergence of methylotrophic biosignatures, isotopic evidence of methanol metabolism in organic matter, or increases in cyanide-resistant bacteria in environmental samples. Coordinated atmospheric monitoring and ecological surveys would be needed. None of this is happening systematically. Sober assessment, spectacular to imagine, extraordinarily difficult to execute or detect. This leads to a final, pivotal question. What if 3I Atlas isn't delivering a payload, or terraforming, or poisoning? What if it's doing something even more fundamental, testing? The 3I Atlas intelligence test. Is the object probing before acting, rather than delivering anything? What if its mission is purely reconnaissance? A low-risk assessment of planetary environments before any commitment is made. A scientific probe evaluating a biosphere would measure atmospheric composition, O2, CH4, O3 as biosignatures, oxidation states, chemical energy available, seasonal variability, climate stability, and magnetic signatures, radiation protection. ALMA data shows time-variable production rates for methanol and cyanide, but this could be explained by rotation or thermal cycling. Variability is not intent. True signatures of probing would be more telling. Targeted venting increases when close to specific planets, jet pulsing correlated with planetary alignments, non-random orientation of active regions toward targets. Natural processes can mimic some of this, but a pattern would emerge. How would we test for this? With an aggressive observational campaign, high-cadence spectroscopy looking for non-rotational changes, polarimetry to detect organized dust alignment, and coordinated monitoring with solar wind satellites to see if venting correlates with specific plasma conditions. This brings us to the broader, shifting cosmic landscape. In December 2025, a neural network breakthrough demonstrated that stellar chemical abundances could be inferred from simple light curves, no spectroscopy needed. This changes everything for remote assessment. If a probe carried such an algorithm, it could have assessed our sun's composition, deduced the likelihood of rocky planets, and identified Earth as a candidate long before arrival. The technology exists in our labs now. Furthermore, 2025 constraints on quantum gravity suggest space-time is smoother, less foamy than some models predicted. A smoother space-time allows for better long-range coherence. Signals, particles, and objects can travel farther with less scattering. It makes the reliable transport of chemical wakes slightly less implausible. Simultaneously, strange, ordered filamentary structures were detected in a pulsar wind nebula, structures more geometric than turbulent plasma should allow. This hints at natural self-organization mechanisms in plasma that could act as magnetic channels, guiding particulate flows over astronomical distances. If 3I atlases charged wake couples to such structures in the interplanetary magnetic field, it could be funneled, not just dispersed. The final piece comes from the lab. A 2025 breakthrough showed that methanol, under pulsed radiation mimicking space conditions, can produce RNA precursors like ribose and nucleobases with startling efficiency. The plume of 3I Atlas is such a reactor, irradiated by solar UV and cosmic rays. It may be manufacturing the very building blocks of life in real time. And new evidence from Mars' orbit shows complex organics drifting in the exosphere, proving the solar system is a chemically connected ecosystem with dust and organics exchanging between worlds. The big picture. 3I Atlas is a door. It forces us to confront questions we've avoided. Natural wonder, hazard, or invitation? We don't know. The chemistry calls us to look harder, to think deeper. We do not know if we will be fertilized or fumigated. We only know something is coming, and December 19th is when we start to find out. Perhaps the answer won't be binary. Perhaps the universe doesn't deal in simple categories. Gardeners versus killers, friends versus enemies. Perhaps it deals in chemistry, in potential, in reactions that unfold over timescales longer than civilizations. Perhaps 3I Atlas is neither savior nor threat. Perhaps it is just a comet doing what comets do. Or perhaps it is something else entirely, something that will redefine what we think is possible. Either way, we are about to find out. December 19th is not the end of the story. It is the beginning, and we should be watching.